This is part 3 of the graphical item analysis using non-parametric curves. This time I focus on SPSS and with a bit more detail in this brief webinar. I want to remind us that we're using the CSD. I have 600 respondents we saw in part 1 of the video and again in part 2. It's a 20-item measure of depressive symptomatology on a rating scale from 0 to 3, which the respondent is instructed to circle the number to indicate how often they felt or behaved this way during the past week. Everything from 0, not even 1 day, 1 or 2 days, 3 or 4 days, or 5 to 7 days. In the item analysis, to remind us, we do the classical analysis. This is the classical sort of approach. There's the average, which is, something about the central tendency of the distribution of the item. Sometimes we might call that difficulty in a knowledge test. And then we have item discrimination for each of the item and the standard deviation. The item rest correlation, or the corrected item total correlation, is one quantifier of discrimination. There are others in the classical approach, but the guide here is that we use one number to try and give us a sense, for example, of the discrimination. Point of this whole webinar series is that we should supplement this with a graphical display. And so in parts 1 and 2 of this webinar topic, you saw several examples of using scatterplot smoothing, this LOESS, or this sort of locally weighted regression plot. That's a very intuitive way of doing it. It's not ideal. It's not the last word by any stretch of the imagination. The idea is that we're continuing to develop our appreciation for understanding the performance and putting a psychological interpretation to the performance, the item responding, by taking into account a continuum of variation. As we get stronger with those skills, we will find ourselves beginning to use these ideas more and more to develop explanatory theories, eventually learning more, and perhaps later learning more advanced psychometric analysis approaches, for example, like item response theory, parametric or non-parametric item response theory, Roche analysis, etc. I want to say a little bit about these LOESS smooth scatter plots. John Starmer on YouTube on Questat has an absolutely wonderful video titled LOWESS, and LOWESS clearly explained as 3 exclamation points. And he does a terrific job explaining the core ideas, giving you an intuition. So for example, in his example here, you have a scatter of data, and what these local, right? So the idea is a locally weighted regression plot. Is you take the data, in a sense, you create this sliding window of a particular length that covers a certain number of points, for example. And then you run a regression, depending on the kind of smoothing we're doing. It could be a weighted regression. And you move it along in the sliding window, and then you connect all of these, and you get a smooth line. Take a look at it. It's actually an extremely intuitive description, and John Starmer does a great job in it there. Today I want to just add a bit more to what we did in parts 1 and 2, where you saw several examples, and I want to say a bit more about doing it in SPSS. And, describing this sort of smooth scatter plot approach and giving you a sense of what some writers will call the span, within a sense, is a sense of the, in a way, is related to this percent of the data for each of these sliding windows. It's very computer intensive, but what I like about the LOESS approach, and many people do as well, is that it's actually fairly intuitive, it's fairly fast. Depending on the software you're using, you can even get standard errors. etc. And it's a very powerful tool. Last time in part 2, you saw me describe it in using R, particularly using a flex plot in the Jamovi interface. Today I want to focus on SPSS and give you a sense of the percent of data option in SPSS is related to the span. And the span, or the percent of data, controls how much smoothing is performed. A large span results in smoother but less locally fit functions, and a small span results in rough, very higher variability, and more locally fit functions. So if this is covers a lot of percentage, well, it's actually smoothing. It'll actually smooth out. It'll miss some of the pattern in the data, but it'll be very smooth looking. You'll see the eventual line that's connected here would be very, very smooth. And if these are very small, right, the span is a smaller percentage, you'll see lots of jagged because it's actually capturing a lot more of it. And there's, sort of a bias variance kind of trade-off that goes through all of this. All right, so let's take a look using SPSS and see what it can do for us. All right, just to be clear, I'm going to use the total score as opposed to the what's called the rest score, just to allow us to make the interpretation a little easier, but we'll come back to that in a moment. So the way I do it is I use it through legacy graphs. It's fairly easy to do. You can get syntax. If you want, you can run it in R, you can run it in Jamovi. This is SPSS, so I go through legacy graphs, SCATTERPLOT, simple SCATTERPLOT. So let's take a look at the first item. That's on the y-axis, the total score on x, and let's put as a marker whether the participant or the respondent identifies as male or female. Let's just start with that. You'll see here now, the nice thing about this video is that we don't pop between windows as SPSS does, but we should be able to see all of it at this point. You'll see the graph here. There's not much of a pattern. The item 1 is during the past week. I was bothered by things that usually don't bother me. That's a very interesting kind of graph. You see we double click on it, that comes open. We go to elements and we can fit it for the whole group. What can we fit? Well, it automatically fits the straight line. You can see it right there. That's what the default is for the scatter plot. Let's use the LOESS approach, and let's use the default kernel here. We have several options, but let's stay with this one for now. Let's apply it, and you'll actually see the graph change in this way here. What's interesting is if you were to, let's say, increase this to, let's say, 90% to fit, so that those blobs, in a sense, cover more and more of the data, a wider amount of the data, you'll see that actually it's very smooth looking. It's smoothed out all of the little bumps. And if we move this down to, let's say, 15%, you'll see it actually follows a lot more with the range of the data. You want to see the pattern, but you want to get a nice trend line. There's this sort of variance versus bias kind of trade off here. I think actually it's probably not it'll depend a little bit on the shape of the distribution of the X score here. This is actually becomes quite important because you'll see the distribution here could result in some very sparse data, and you saw this in part 2 of the video. There's not a lot of data, and you can even see it. Most of the data, because this is a depression measure population in a general population, people are going to score very low. So why don't we stay with, let's say, a 40 or 50%? There gives us some nice smoothness. Doesn't become too erratic, but gives us some nice pattern in the data here. But what you see is it starts quite low, and then it makes its way up. That's sort of the general monotonicity. This increasing is what you want to look for, as individuals who have higher levels on the CSD should be responding higher there. If not, the line were flat, it wouldn't be discriminating. So you see here, it's quite nice and sharp like that. If we were to fit a straight line, actually, it would look like that. That's interesting. So we can do it that way, I think, but this ignores that some respondents this ignores that some of the respondents identifies male, others identifies female. It becomes interesting because there is a literature. I'm not a specialist in this area. Let's do it again here. Create another graph. It's easier to start over again. And what we can see, going back to elements, now we'll fit it. There is some literature that says that there may be a difference in the overall scores of individuals who identify female versus the ones who identify as male. It's unclear why that's the case, but if you stay as a straight line, you can see that, well, actually, they're quite close up to about almost nearly 20. Then there's a slight difference if you were to force a straight line through the data. If you let the data give us a little bit more input as to where the line should go or where the curve should go, now you have this kind of idea going here. It's kind of fascinating. I'm not sure that's a very good graph, to be honest with you. And it's let's try with the tri-weight, because there's a lot of data here. Take a look at that. Actually, this item shows something quite interesting, right? Again, we can go to it and we can work with the kernel smoothing as we had there, 50%. That's a very fascinating. You'll actually see the equations. You're actually fitting, very curiously enough, you actually fit this expanded model. That's kind of what it does there. You can see that those are quite fascinating from it that way. Those are the quadratic versions in here as well. Let's go back and fit the same thing again. And I like to start over because SPSS is not particularly welcoming to editing their graphs. The software is a little finicky that way. But if we double click on it, we bring up the elements, we add the sublines groups there. Let's use the tri-weight, or we could even default with that one there. That's not too bad of a fit that way. But look at it. You actually have a point where there's a lot of very close here. These curves are very, very oddly behaved. Although if you look at this, this is actually quite fascinating. What this is showing is that for individuals who identify as female, which is the blue line, right, during the past week, I was bothered by things that usually don't bother me. Well, actually, individuals who score the same on the measure, actually, is above 25 nearly. They cross over. There's a bit of a difference in here, half a point. It's an oddly behaved item in this way. I'm concerned about the LOESS smoothing, but you can see it there. I might play with the LOESS smoothing a little bit to see if I can get a better fitting line. Let me get rid of the quadratic. Let's see if it'll allow me to do that. And instead apply the tri-weight, which downweights, as we talked about in part one there, it sort of downweights the extreme points, so it's a bit more robust. We now have two versions of it there, and actually what this shows me is actually an interesting picture, is that in fact, whether you use the tri-weight or you use this particular kernel here, you're getting very close looking curves. Gaussian is going to be interesting because the Gaussian one is, I probably wouldn't use it at this point. you can see that it's going to give you a very kind of an odd, different looking line there. So you can now see, actually, it's not too bad. I'm not sure I can even discern some of it. So the Gaussian is, our pattern's pretty good here. If we try to smooth it out a little bit by maybe going up to 60%, so that in essence, if you think about it, they cover more of those spans of the window, those little subgroups, those that are those little bubbles across, cover a larger part of the data. It smooths it out a little bit. That's kind of interesting there. But there's not a lot of data up here. So be very careful. But now what you're seeing is quite a bit of a 1 point difference way up in here. It looks like this item, one interpretation, although I do it cautiously, bringing the psychology into the psychometrics, if you wish, is that at the higher levels of depressive symptomatology on the CSD, individuals who identify, respondents who identify as male, tend to endorse or to provide a response closer to 3 than individuals who identify as female at pretty nearly the same level of depressive symptomatology. It's a very interesting kind of analysis. Shall we try one other item, and then we'll pass it on. We'll do it again, and we'll go to SCATTERPLOT. Let's take item, I don't know, let's say item 4 this time. Let's try the same kind of idea. Right now the item is, during the past week, I felt that I was just as good as other people. Oh boy, this is going to be an interesting one. Double click on it, you'll see the window comes up. You go to Elements. Let's just go directly to fitting it for both. Look at this. If you look at the straight line, it's saying, well, the response function, if it were straight, is about the same for individuals who identify as female and individual respondents who identify as male. If you apply, again, a similar kind of message. If you apply if you look at this different kind of kernel, you can try a tri-weight kernel as well. And you're seeing very close looking sort of patterns in through here. These are not large amounts. We don't have confidence bands along these. It would be kind of nice to see. SPSS is not particularly good at the confidence bands for these. SPSS has a lot of power in a lot of interesting ways. Its graphics are particularly through this interface. There's a more sophisticated interface one could go through. But nonetheless, it's saying, let's not just look at one number. Let's instead look at these, if you wish, response functions, knowing that this is the total score. What we could do now is just go to the raw data again, and the total score is, it's a very intuitive way of looking at it. We could compute a rest score, if you wish. So let's call it MH, and let's do it for the first item, MH1 rest. So let's call it, actually let's change the name, call it CSD MH1. So this is the CSD. Now what we would do here is we'd take the total score of the CSD, we would subtract from it the item response that the individual gave for the first item. So it's right, and we'll use this for the plotting of the first item. If you take a look at the data and scroll it over to the side, you'll see there's a new score called CSD underscore MH1. And you can see for this first person, the first 4 individuals gave a 0, and then the 5th one gave a 1, If you look at the CSD, those should be the same except for this respondent here, for whom it's going to be one less. Well, if we want a closer picture of this, if you wish, item rest correlation, would have, let's start it over again. Let's reset it. Let's put MH1 there, and then let's see the corrected CSD score for MH1. So this is the CSD total score, removing item 1 out of it. It's something akin to what you would get in the corrected item total correlation. So this, in a sense, there's no double counting that goes on here. There's one way of thinking about it. If you take, let's go directly to the subgroup analysis. If you look at the straight lines, very close, right? Those are the R squareds. Actually, those are the, if you take the square root of those, you'd get the something very close to the corrected item total correlation. But let's fit a curve to it instead. So this is, if you wish, a more purified continuum along here. Of course, it would change from item to item, so it's because, you know, it'd be the CSD minus item 2, CSD minus item 3. So the item on the Y would be removed from there. All right, that's interesting. This pattern is actually, what you find is that there isn't a great deal. The pattern is still sort of same as what we found before with the total CSD, that you get this difference in that range. It is a bit closer, however, to what you would find in a corrected item total correlation, if you wish. One last thing that you could do is, let me just describe this. These are all, none of these are perfect, and what you're trying to do is get something more than just a single number. And this, I'm hoping, will lead us to even more efficient ways of looking at this problem and getting you start thinking about this item response curve. Well, what if we took all 20 of the items, and let's do a component analysis. Fine. And we'll save one score, one component, because we're going to add it up to a total score. All right. If you wish, we can even take a look at a scree plot to see if it gives us some sort of interesting pointer. Let's save the variable, and the regression predictor of the component score is a sufficient start. I think it's again, we're not looking for optimality. We're trying to learn to get an intuition for how to think about and how to use these kind of scores. And just so that you see, there's now a new thing called Fact 1, right, which is really the first principal component. SPSS confuses factor analysis and components, but nonetheless, that's the first principal component. Just to see, so you can get a sense of what it looks like. Let's actually take a look at it. Let's do a histogram of it there. I'm not going to print all the values because there's a lot of them. We'll give you the mean, the median. Sure, standard deviation, minimum, maximum. Yeah, some sense of the kurtosis there, I think, would be valuable too. Just so you can see what it looks like. And this is a graph of the factor score. And in fact, it has a similar kind of shape as the original data. That should be, if you think of this as a transformation in this component space, it should have something like that. It has a mean of, well, that's minus 16, so it's really 0. So if you think about it, it's like there's like 15 zeros before this number and a standard deviation of 1. So it's actually standardized. It's a standardized score. Mean of 0. Median is negative. Now, why is it negative? Well, because you can have it's a z-score or z-score metric. Curiously, no one, because of its skewness, the lowest possible scores that are available in the data, that realize the data, is like -1 standard deviation. It's a way of saying, look at the shape of this distribution. The skewness is 1.628. The way it's scaled is hard to make a lot of sense. The kurtosis is 2.9. But the idea is you can take a look at this. Now what you can do is you can go back to your scatter plot. And instead of having the CSD there, for example, let's put in the factor score. Is this perfect? No. Is it efficient? No. Is it intuitive to get you to start thinking in this manner? What we've changed here is we've rescaled this. And if we now click on it, if we now double click on it, and we go to, let's just fit the overall one first. Let's do the LOESS one. You can see the pattern's not that different. Actually, there's a little bit of a smoothing up, but you can take a look at where all this data is in here, how little it is there. We can close this. Let's go back to, actually, we can go back to it if you want, and do it for the subgroups as well, and add the LOESS. In the subgroups, this is the plot's a little noisy, but you'll get a sense of it. So the one in black ink there in black font is overall. In green is individuals who identify as male, and blue is individuals who identify as female in the respondents. That's a very interesting. I do that. The problem is trying to interpret this, because now it's in a z-score or z-score metric, etc. But it's good to start getting this, to get an intuition for this and to start working on it that way. I hope you're enjoying this. Take care. Thank you.